Thank you, everybody. Good afternoon. We are really happy that you could join us today. My name is Arpan Shah. I am the engineering manager on the data team at Robinhood. And with me, I have Sayam Setia, who's a data engineer, and Grace Liu, who's also a data engineer on the Robinhood team. So for those of you who don't know, Robinhood is a commission-free investment platform that allows you to very easily buy and trade cryptocurrencies, ETFs, stocks, and options. Our mission is to democratize the American financial system, and making data-driven decisions is a big part of that. So that brings us to today's talk and why we are here to talk to you about data lakes. A data lake is a central repository that a company maintains for structured and unstructured information that allows the company to make decisions and acts as a platform for other tools and technologies that need the company's data to be built on top of. So we have a packed agenda for you today. We'll start talking about the journey that Robinhood took, why we felt we needed a data lake, what are some of the decisions that we had to make, the architecture that we finally came up with, and finally, we'll talk about a lot of the learnings that we've had that we hope will help you guys build your own data lakes as well. And in the end, we'd love to take any of the questions you have and help you guys think through any of our tech stack or any of the decisions that we've made. With that, I'd love to hand it off to Sayam and Grace, two of the key engineers who helped build this data lake. Thank you.
Thanks, Arpan. So, as Arpan said, let's start by diving into the problems we saw before we set out on this journey to build the data lake, the patterns we saw emerging at Robinhood, and how we actually ended up dealing with these. So one of the basic problems that we saw that doesn't look like a problem at first is that we had several data stores at Robinhood, and all of these are optimized for their needs. We have a Redshift instance that is basically storing a lot of events and analytical data, and it's really good at doing that, really good at compressing all of this data and answering queries. We have Elasticsearch clusters that is working as our document store. It's really good because it's based on Apache Lucene and acts as a search engine. So our in-app search is something that is powered by this and is really efficient at doing that. We have InfluxDB, which is our time series database. It's really good at answering time series-based questions, ingesting large amounts of data in a small amount of time, and answering questions on top of that. We have S3 as our object store. We have Postgres as our relational database, several of these used by different services for their relational needs. We have Dropbox for sharing files within the company. There's several third-party integrations we have for getting to certain points we want within the company. The problem that comes into this is not their primary work, it's the secondary workflow that comes with these systems, which is usually the analytical purposes. Whenever a data scientist wants to do something interesting, build models on top of this data, or do some in-depth analysis, the problem that comes in is that they usually need to go into multiple systems, pull the data that they need, aggregate into a central place with lots of memory, lots of compute, and do something over there. Let's take an example of what this would look like. So let's say a data scientist wants to aggregate our events data with some relational data and have some documents that we are storing in Elasticsearch and work with all of them at the same time. Now this becomes really problematic because the person has to ramp up on the different dialects each of these data stores are speaking. While Redshift and Postgres, you can just use SQL. For example, Elasticsearch uses Lucene query syntax, which is not trivial to ramp up on in your first go. So not only do they need to learn about all of these different things, they need to pull it down to a central location, for example, their local disk, and then they have to upload it to a box with ungodly amounts of CPU, ungodly amounts of memory, so that they can do some transformations, join these data sets together using something like a pandas data frame. Another problem that we started seeing as we started growing as a company, internally with our internal data users, and even externally as we started rolling out Robinhood to more and more people, started launching more and more features, is that we saw like things turn from gigabyte scale to a terabyte scale. We saw our events data set go from a few gigabytes per day to several terabytes per day. We saw our ALB logs, which is our Amazon load balancer logs for different services. As we started scaling up from like few handful services to like tens and hundreds of services, we saw this spinning out of hand as well into the terabytes, into the petabytes. And this becomes really problematic because the system we had previously was basically that a single system would go and read the data that it needs to do some transformations. And so the only tool or the only lever we had in our hand was to vertically scale up these systems as we got more and more data. And as the data users within the company grew as well, there were different applications that they want to do, and some of these are not really trivial to be doing with the bottleneck of a single box. let's take a look at what the problem at its core looks like. The problem at its core, as we analyze further, is that we were using systems like Redshift and Elasticsearch, which are great at front, but as the problem with these systems is that the compute and storage you have in these systems is kind of very closely coupled together. So compute would increase when your applications, your queries are increasing, which is your internal data use is increasing. Storage would increase as you start offering more and more services, you start getting more and more users. The problem is that, like, even though only one of these things would usually increase at one point in time, we would have to scale the system up to handle large amounts of load on both of these axes, which becomes really prohibitively expensive. And we saw really big slowdowns among our Redshift and Elasticsearch clusters because they were having trouble operating at that scale as well. Robinhood is a company that is largely driven by the data team. It's a focal point within the company, and a lot of different teams go through with this. An example you can see on this particular slide, we work a lot with the compliance team, which works in turn with a lot of regulatory agencies within the finance industry. Since we work in a highly regulated space, they need to find out a lot of information whenever such regulatory requests come in and access our data stores to get this information to regulatory authorities as soon as possible. We also work with the brokerage team, which needs access to a lot of trade data. They also need access to a lot of quotes data to see what the price was at a certain point in time. And we have accounting and business teams, basically, that would be using a lot of our financial data that we are storing in-house and need to work on top of this. Currently, the system is that all of these requests go through data scientists, which end up becoming a bottleneck for all of these people doing their day-to-day jobs, which is not ideal. And it's really not trivial to ramp up these non-technical users onto our systems, since there is actually a lot of technical knowledge involved into going on a lot of these systems, pulling the information down, understanding the dialects, and using complex mechanisms to achieve what they want at the end of the day. Another thing that we always want to strive to keep getting better at is better privacy controls, better security in-house, and making sure that the data is accessed by exactly who needs the data. Previously, we had a system where we had a single research environment, and this research environment basically had access to the systems we wanted to access the data from. For example, if there's a Postgres instance that we would want access to, this system would be able to talk to that. The problem is with this particular instance is that there would be very coarse-grained access controls. So you can decide whether or not to give access to a particular system, but as soon as you start diving into table-level, column-level access, that gets harder and harder for the security and the development operational teams to keep track of and maintain as we move forward. Another issue that we saw over there is that as people log onto these boxes and make queries, the queries essentially get masked by the research system itself. So when we see on the data store, we saw that these queries were run by the research system and not by the individual user who ran these. While it's still possible to tie these two together by looking on the logs on the box, this is something that's not trivial to do and is really cumbersome to do on an ad hoc basis for our security and DevOps teams. So to summarize, there's a set of problems that we wanted to, that kind of set us out on this path to look for a data lake solution. One of these was that data was really fragmented across multiple systems. There were compute limitations whenever we were working with large amounts of data, and as these data sets scaled, these problems just kept on getting bigger and bigger. And at the root of that was the issue that scaling this infrastructure the way it was set up initially was becoming prohibitively expensive and was also becoming inefficient. So we were paying exponentially more for the service that we were getting in a linear space. We also wanted to get finer-grained ACLs that were not only easy to set up, but easy to manage as we moved forward, as we created new divisions within the company and created new access levels that we wanted for our different users. So the data lake at Robinhood solves a lot of these problems to varying degrees. It solves a lot of these problems in the sense that we can now process large volumes of data in a distributed fashion by using distributed computation frameworks. Allowing these different distributed computation frameworks to work on our data gets rid of the vertical scaling bottlenecks that we were facing before. Now, if we want to process more data, we basically just add more boxes to a cluster of community hardware that we're just using, which makes this problem a lot more tractable. We're also now providing a unified query layer to our users. What this means is that the users can now just straight away access the data that we're providing in the data lake. They don't need to worry about whether this data is coming from Postgres. They don't need to worry about whether this data is coming from Elasticsearch or some other instance store. All of that is abstracted away, and for users that even knew this, there was a lot of repeating work that we just took away from them. And we said, rely on us, we'll provide this for you. You only worry about the analysis part, since that's what primarily their job is. This also allows our security and development operational teams to manage our ACLs at a very finer grained level, allows us to isolate on a query level to see who exactly ran this query and gives us better tracking in that sense. So let's start looking into how we went about solving these problems. So before we actually started writing any code or before we started just ramping up towards like how we want to build this, we actually started out doing some research. We were quite sure that we're not the first company to face problems like these, and so we wanted to take some inspiration from bigger and more respected companies in the tech companies to see how they had tackled these particular problems, and if we could take some cues from over there and come to a good solution for our company as well. So you can see a lot of big names in the tech space over here. Netflix, for example, used Presto to query over and store terabytes and petabytes of data, which was really inspiring to see. Uber, for example, used Parquet at a really grandiose scale. They contributed a lot back to the open source community as part of their exploration on this project. Finra is a company we closely work with and has similar workloads to ours, since they're also in the finance space. So it was really interesting to see how they were able to use a data lake to solve some of their problems over here as well. Then we went and looked at a lot of AWS documentation on how we could build solutions like a data lake using managed and serverless solutions that AWS provided. This was really important for us at this point in time because when we were starting out on this journey, we were really unsure whether this was the right path. There were several solutions we were comparing and contrasting with, and data lake was one of them. We really wanted to be sure that this was one of the things that we wanted to do. And in order to do that, we didn't want to spend a lot of time doing this since most of us are working at startups and all of us can empathize, our resources to work on a single project are quite limited. We didn't have a lot of Hadoop expertise in-house. So we wanted to get off the bat quickly with like minimal overhead as much as possible. And AWS managed and serverless solutions provided this for us. We didn't have to set up our own clusters. We didn't have to deal with version conflicts. We didn't have to deal with a lot of overhead that comes with maintaining and moving forward with these technologies as time goes on. So that was a good starting point for us to try and test how things would work and how things would look in an ideal scenario. So this is what our architecture looks at this point in time on a very high level. It's very important to note at this point in time that there is no one data lake fits all solution over here. Trust me, we looked. And if there was a simple solution, we would have probably gone with that instead of like building a full-fledged architecture, but the simple truth of the matter, as most of you already know, there's no one way to solve such a complex problem. The truth of the matter is that like, each of us at our companies work with a different set of systems. There's a different set of problems we want to solve, and there's a different set of clients we want to serve. And so there will be different solutions that people will come up for different companies. So we have 6 layers in our architecture over here. We start with the ingestion layer, where we take in a lot of data. We store it in the storage layer. We then do some processing ETL jobs on top of that in the processing layer. We allow this data then to be queried using the query layer, a couple of tools in there. We then do some validation on top of this framework. And then we allow the user-facing layer, which is the layer most of our users interact with, to actually go into and look at this data and interact with it. Let's start with the ingestion layer. So before we build the ingestion layer, we set out on this journey to understand what the ingestion patterns at Robinhood or the data piping patterns at Robinhood were. We saw that they were categorized into 2 major categories. One of these systems was a streaming framework. Essentially, we leverage Kafka very highly at the company, and it's a system that we use as a buffer between our different services. Every service that is computing something will basically output a Kafka log, and other services that are downstream of that service will consume that and operate on top of that. Since we saw several such use cases, we even built an in-house computation framework on top of streams, which we call Faust, and is open source. And if you're leveraging Python and Kafka highly at your company, I do recommend taking a look at that. Something we had set up long ago, because we highly use Kafka at our company, is a CCore pipeline. CCore is an open source library offered by Pinterest that allows us to archive our Kafka topics into S3 in a reliable manner. It gives us some really good guarantees that we were really happy with, and this is a pipeline we had set up long ago. Another major way of getting the data into the lake is through batch jobs. We have several batch jobs running that fetch data from external integrations, like Adjust, which we work with for our ads data sets, Zendesk, which we work with for our customer support data sets, and then there are like some use cases that come up with the data lake itself, like our RDS snapshots that we take and put into the lake. And all of these, at the end of the day, are stored in our storage layer. So let's take a closer look at what that looks like. At this point in time, we chose Amazon S3 to be our storage layer, simply because it's simple, it's in the name. And another issue that we wanted to resolve by using S3 is that other alternatives we saw in this space, which were like HDFS, again, are really hard to get off the ground with when you have a really small team working on such a big problem. S3 also builds really seamlessly on top of all the managed and serverless solutions that we saw that AWS was offering and that we could leverage to build our data lake. The way it works right now is that we have an ingestion layer that basically puts data into this S3 bucket we have into a raw path. Once data is put into this raw path, it then interacts with the processing layer and puts data back into a columnarized format for large and immutable data sets. There are certain use cases where we actually want to work with mutable and hot data. What I mean by hot data over here is data that is accessed very frequently by a lot of different services, by a lot of different dashboarding tools that we want to build on top of the lake. So that data we prefer storing into Redshift to get sub-second latencies on top of that data. Before we set out on doing this, we actually want to do some back-of-the-envelope calculations to see how much better this would be than our current solution, if at all. So the one test case we kind of played around with is that if we were to assume that our events data was 75 terabyte compressed using Parquet and Snappy, we found out that if we were to store this data into S3, it would cost us about 21 grand per year. And if we were to store the same data into Redshift and just scale up the cluster to whatever size we needed, it would cost about $1.2 million. Even though this looks like a really big number, let's not discount Redshift right away, because Redshift allows you to query over this data as much as you want. While S3, you cannot just query the data directly. You need some kind of tooling on top of that. We provide that tooling to our customers using Amazon Athena. Athena has a cost in itself. We saw that it costed $5 per terabyte to scan over data that it used in order to answer the questions you wanted. So if we were to aggregate these two together and assume that every person were to query some ungodly amount, like 1% of the entire events data set, which they usually don't because it's a really huge data set of spanning over several years. But even if we were to assume something like this, we saw that people had to make close to 250,000 queries per year in order to get close to this amount we were paying at Redshift. Since we are a very small data team, we saw that we were at a very small scale compared to this, and this would be a really good place to start off at. And if we found that we were getting closer to this level, we could move to more complicated or more streamlined solutions exactly for this need, because then we would have a demonstrated use case for this to show to our engineering leaders. We could move to solutions like Presto on EMR, which would reduce our costs and allow us more flexibility once we were sure that this was the right way to go about it. Let's talk about the processing layer that interacts with the storage layer and the query layer. This is where a lot of the magic happens. We are really lucky since we already had Airflow as our workflow composer and scheduler at Robinhood several years ago before we started on this journey. Airflow gives you a lot of neat features that we really appreciated. If you're just a Unix shop running cron jobs, I understand that Unix is really streamlined, it's really easy to use, but there are some things that Airflow doesn't offer in its manual that you kind of learn later on down the road. Things like when your jobs fail, finding out about these job failures, rerunning these jobs is a very manual and cumbersome process. You SSH onto the box and then do something over there. This increases operational overhead, and since we are a very small team, we want to go on and build as many things as possible, as many cool features as possible for our users, and this kind of held us back. So having Airflow kind of solved a lot of these problems because Airflow has built-in retry logic. It also allows for things like exponential backoff so that you're not overwhelming your upstream services and are making sure that you're giving them enough rest time between querying again and again. It also offers a way to define dependency between different directed acyclic graph jobs that you might have. It also offers a lot of flexibility in this sense because basically you define your workflow using something like Python, and it's really extensible at that point in time because what you're limited by is basically what Python can do. It's also really cool that there's a huge community building and developing on top of these tools and releasing these every month. And so that allows us to build on top of the operators and connectors that are already available out there and just build this project on the shoulder of giants instead of reinventing the wheel from scratch every time we need to do something new. The usual way this workflow would work for us at Robinhood is that first we would go on to the schema discovery step. This is one of the first steps that would run as part of a new job. For schema discovery, we use a tool like AWS Glue crawlers. What a glue crawler is basically a system that scans over your data and tries to find out what the schema of your data set is. What this would involve is metadata related to your data store. It would see what columns you have, where these are stored, what partitions you have, and basically just find out some neat little details and put them into the Glue data catalog. And these would later be exploited by the Presto or the Athena layer in order to make more efficient queries on top of your data. Then we would go on to the Spark layer to do some of the computation. Over here for our distributed computation, we chose Spark for several reasons. One, it's really flexible, it's really extensible to build on top of. There's two development experiences it provides. One is Python and one is Scala. And since we run a primarily Python workshop, this was right in the wheelhouse of our engineers, and there would be minimal overhead in learning this new technology. Another thing that is really good over here with Spark is that it allows distributed computation and is in memory. So that means that it's really fast as compared to some of the other solutions we were looking at, which would spill to disk every time between different stages of the process. And it has really good retry logic if some stage fails in the scheduled task it had produced. There's two ways to leverage Spark within an AWS ecosystem. One of them is AWS Glue. It's a managed and serverless solution provided by AWS. And this is really good because it lets you get off the ground without customizing a lot of things. It gives you common sense defaults. And all you need to do is just feed it your Spark script, and it will do wonders with your data. However, there's not all use cases that can fit into the Glue pipeline, even though most of our use cases are good with this. There's some use cases where we think that EMR is better suited for our needs. Use cases where we want fine-grained control, where we want executor logs, where we want to know how much memory is occupied for each partition. We want to vertically scale up our instances. We want to horizontally scale. I want to change the yarn configurations. These instances don't come up very often, but whenever we're working with really large data sets, for example, when we were backfilling the events data set at Robinhood, which was close to a petabyte, we thought that EMR was the right choice, and we basically used it to work over huge amounts of workload and backfill close to a petabyte of ALB log and events data set at Robinhood. And that kind of feeds back, once it has done the processing, it feeds back into the storage layer, into the same bucket. And we run a crawler again over the same data at the end of the day to find out what the final schema for your data set will be. This will primarily be same as the raw schema in most cases, but your processing job could do some transformations that make it appear different. Since I also said there are some neat features that the Glue crawler will look for your data, when it stores it into metadata catalog. This includes compression that you're applying on your data and columnar encoding formats like the one we're using, like Parquet. These will all be different and will help the query layer in the future to make better queries, make faster queries on top of your data. To enlighten us more on top of that and to discuss our architecture and the next steps at Robinhood further, I'll pass on to Grace.
Hello, everyone. Hello. Hello, everyone. This is Grace from Robinhood data team. Now, let's come to our query layer. So our query layer is the layer allowed you to query the data stored in our storage layer. As we mentioned before, we have two major data stores in our storage layer. So for data in Redshift, you can directly query through Redshift since it has built-in query engine with it. But for data in S3, we use AWS Athena, which is AWS managed serverless Presto. Presto is a distributed SQL engine, allow you to query the data in where it's stored without moving data to another analytics data store. So like as we mentioned before, we use Glue crawler to detect the data schema for the data stored in S3 and write this metadata to Glue catalog, which is a Hive meta store on AWS. So then Athena can use this metadata information in catalog to query the underlying S3 data directly. So since Athena you charge us by how much data you scan per query, we also use a columnar format Parquet to optimize the query performance, also reduce the data size we need to scan. So this is the query layer. Let's come to our validation layer. So during the time we are building our data lake, we realized there are lots of silent failure might happening in our pipeline. For example, like you might see all your jobs succeeded in Airflow, but you still ended up with incorrect or incomplete data in our data lake. It might because of some unknown upstream failure or just some hidden transient error in your pipeline. And this is actually very bad because the only way you can discover it is at the time you actually try to use it. And it's like we also during the time we want to build our data lake project, we did lots of research, not only in the successful example in industry, we also research on how data lake project fail in other company. We see that the major reason of the data lake project fail is because people lose trust in the data lake. Like for example, like people just randomly dumping data into data lake without actually understanding and check the data. And the downstream users soon realize that all the data in data lake is not very reliable, and the internal users stop using data lake. So this make this project just become meaningless. So we are aware that it's very important for us to ensure the data quality before we ship to any downstream service or downstream user. So that's why we build this validation layer to check the data quality. So this validation layer is a kind of extensible framework for you to define different kinds of check for each data set. So it's connect to our query layer. So it allows you to run validation query in our underlying S3 data set to check if data is correct or the integrity is good. So let's take a look for some common basic quality check we have for our data sets. Like for example, we have record count and null count. For example, like if you have like 1 million events per day usually, but today you just see 20K events coming, it's definitely worth you to explore if there's anything wrong in the pipeline. And also the partition. If the underlying data is partition data or the partition table, you will expect to see new partition landing after today's pipeline finish. So you might also want to check that. And also the similar idea, distinct value and unique constraints. Sometimes some column in some data set should be distinct and unique. For example, like the user UUID. So you might also want to verify it. A part of all of these common checks, we also allow you to do some user-defined checks for your own data set. And this might be better fitting to your own use cases. So since we have this validation layer, we only ship data to our downstream use, like when all this validation check pass. So let's come to our final layer, like user-facing layer. This is the layer we provide to our internal user for them to access the data and use the data in the lake. One major component of this user-facing layer is our research environment. This research environment is built with Jupyter Hub. It's like Jupyter Hub allow all the users like have this kind of like own server in container and its own like workspace to create and run their Python notebook or R notebooks. So this research environment also connect with our query layer. So you can like fetch data from different places just in one notebook and then do further analysis by your code. And this research environment also like connect with GitHub. So all the notebooks are like what we are keep track of all the notebooks, and all the notebooks are kind of version controlled. So this is the research environment, and another major component of user-facing layer is our BI analysis tool, Looker. So Looker is also connected to our query layer. It also allows you to run like SQL queries, but also lets you build like your own visualization of dashboard in Looker, and it's much more user-friendly to all our non-technical internal users. So this user-facing layer is kind of the final layer on top of all our data lake systems. This is the end of our architecture review. Let's summarize and what we have achieved by this data lake project and what is our next step. So let's start with what we have achieved. One thing like I want to highlight is like previously, as I mentioned, you need to jump in different servers or data store to get and fetch the data. But right now, you can easily join across multiple data stores just by one simple query in a notebook. You can see the example here. Like previously, those underlying data are in different DBs, so it's very hard to join across the database. But right now, you can just join them by one single query in notebook, like through data lake with the RDS snapshot we have. And so this will highly boost up the productivity of our engineers and data scientists. And the second thing I want to mention is the compute and storage are now decoupled. Right now, our very large data set are lying on S3, but we are running our queries through Athena. So we pay for the compute and storage separately. Unlike before, when we just use Redshift and Elasticsearch, we have to keep scale up our instance type while our data grows, regardless we need to use the computing power of this box or not. So this is quite beneficial for our future scaling. You can see the graph here. So when we want to scale up our compute, we usually see the rates of the application increase or the query increase. And also we can just scale up our storage with our user base growth and the data volume growth. Another thing is we now have a feature-rich research environment and also very good dashboarding tool Looker. So this kind of make all the data in our lake become very useful for our internal users. Now data scientists are happy because we make their work easier, and also our marketing and business and PMs are also happy because they can easily visualize the metrics and their kind of the performance related to their job duty very easy. So to summarize what problem we have solved by our data lake project, there are several things I want to highlight here. The first one, as we just mentioned, previous data scattered everywhere, but right now we have a unified interface for various types of data. And the second thing is because previously it required lots of technical knowledge to get the data and work around. So all the data requests need to go through our data scientists to get the result. But right now, no matter you come from a legal team, accounting team, or finance team, it's very easy for you to just access the data and find the answer on your own. And the third problem is previously we have compute limitation for a very big data set. For example, though we have lots of computing worker boxes, but still one single job just run in one particular box. And also when we want to fetch our backend data, all the query runs through a single replica. But now we have leveraged distributed computing for all our data processing process. We have batch job runs through Spark cluster. We have query runs through Presto. So this will benefit our future scaling and also better for our cost control. And the fourth thing, as I just mentioned, the storage and compute are decoupled. It's also for our future scalability. And the last thing is right now we have much more fine-grained access control through IAM roles, because all of your user identity you use in research environment is attached with your AWS IAM role. So what data you can access and how can you access this data can all be controlled through the IAM role permission configuration. And also we eliminate or hide all the sensitive user PII information from our data lake. So this kind of will remove most of the security concern from our company aspect. So let's talk about where we are headed. So a few things we are still working on. One is the data lake usage checking and monitoring. There are some things we want to be aware and kind of prevent the overuse of data lake resources. For example, you might have overuse of the Google crawler. Sometimes you don't have new schema to detect. You don't actually need to run the crawler, scan through all the data. You can just run a simple command to add partition to your metadata. And this is one example. Another is we might have overuse of DPU. DPUs is the computing unit we pay for to run the Spark job in Google. So for example, if you have a job, you can finish in 2 minutes with just 2 DPU, but you still specify to run this job with 30 DPU. So it's kind of a big waste. And also sometimes people run their query their query doesn't follow the best practice. So some data science query might scan through more data partitions than they need to scan. So this will also increase our cost and increase the query time. So these are all the things we want to be aware of and prevent. So in order to do this, we are still working on building a better tracking system to do the monitoring and alerting. And the second thing is we want to have computing at scale for our research environment. So basically, we want to leverage the distributed computing also in our research environment. We want to hook up a computing cluster with research. So in the future, data scientists or engineers can run complex analysis or machine learning model with very huge data set through Spark or other distributed computing framework. And the last thing is we will always continue working on the performance optimization. Like one thing is like for example, we use WLM, the workload management, to manage the Redshift resource allocation to different group of users for using Redshift. For example, we have data scientist group, we have BI group, we have system group. All of these have different configuration of the layer concurrency level and how much memory they can use. What's the best setup here is what we are always learning and keep like updating. And also like how do we formatting our data and partition our data to achieve a better query performance with Presto is also something we are always learning and keep tuning. So lastly, I want to introduce some of the projects we are currently working on, we plan to work on in the future on top of the data lake. For example, the experiment analysis. Lots of experiment analysis can be automated by hooking up with our processing layer and the query layer in data lake. And also the risk compliance reports. Right now, we are able to visualize lots of these reports in our BI tools, and definitely there are lots of business and marketing people run their analytics or build their own dashboard and visualization in Looker. And apart from that, we plan to build our unified machine learning platform on top of the data lake, since right now it's much easier to get and collect the large volume of different kind of data. And similar idea here, we want to use the information in data lake to build a better fraud detection model in the future. So all of this indicate that data lake project become the foundation of all our new future projects which backed by data. So I think this is the all the story about Robinhood Data Lake for now. And this is just a starting point for us to tackling the data problem in Robinhood. We have lots of interesting and exciting opportunity and problem in our roadmap. If you feel excited working on this kind of problem, feel free to reach out. Our team, engineer team, always have opening for excellent engineers. Thank you for listening. We are happy to take any question you have.
All right, we are going to take some questions. And boy, do you have a lot of questions. So Michael's first question is, how do you automate testing of all of your ETL workflows?
Do you want me to take this?
Do one of you guys want to take this?
Sure.
Go for it.
So I think there's lots of different components for this. One part is that we have a central repository where all of our ETL scripts live, and it's heavily unit tested. We do some integration tests on top of this. And once this pipeline, if somebody wants to productionize this pipeline, we basically have something like development endpoint set up for our developers to start looking at the data, what this data looks like, make sure that things they want to do are actually tractable. We have a staging environment where these scripts are first deployed, and we try these out with staging data, which is not exactly like real data, but basically gives you an idea of the scale that these scripts would be working in. And once we are sure that this works, and there's version control on top of these scripts, and that if things don't actually end up working, we can roll back to an older version. Then we can actually bump up the version of the script we're using actually in production to make sure it's using the latest script once we are sure that all of these steps are completed. And some of these steps are automated by an internal tool we use called Jenkins. It's an open source tool that we have set up internally to automate some of our testing pipeline for us.
How do you deal with complex multi-level JSON or XML data with keys or array lengths which vary? For example, those lovely names after marketing campaigns.
Do you want to take this, Grace?
I think for this one, as I've mentioned, one thing is we use Parquet as our storage format. It's kind of have schema. It's also support a nested structure, so it's kind of a handle this case. And also we use group crawler. It also can create the schema which support complex nested structure. So I think this is kind of handled well in our data lake structure.
What about schema changes? So schemas evolve over time. How do you deal with them?
Yeah, for this, as I mentioned, we use Google Crawler. So what Google Crawler does is usually scan through the data, the data path you specify, and it will create a superset of the schema on top of all your data partitions. For example, yesterday you have a column called ID. Today's data doesn't have a column called ID, but it scans through all the data you see. In the past, you have an ID field. It will still keep the ID column for you, but all the new, if you query today's data, all the ID value in this column will be now. It's kind of how it handles the schema evolution.
I mean, you're a financial company. Personally identifiable information is a big deal. How do you scrub that in this whole process?
Right, so I can take up that. So I think one of the things that we've done really well upstream is to make sure that all of our PII data is actually stored in a single database and does not pollute and is not or is not scattered all over the place. So we basically just do not take a RDS snapshot of that particular database. So that makes sure that like our downstream pipelines are completely clean. Another thing that we do in our RDS snapshot phase, since it's basically an Airflow operator that we wrote ourselves, you can specify a configuration of what tables or columns you want to ship and don't want to ship. So it allows you to easily whitelist and blacklist things that you want to do, keep moving on. And I think another thing that can really help with this is just having a really strong review process for whenever like new models are created in your databases to make sure that like we are not putting PII into places where it should not be going. So a strong review process upstream helps us deal with these issues a lot easier downstream.
Why Athena over Spectrum?
I can take this one. Yeah. So one of the big things that we found after doing a lot of research was that Presto is a really powerful tool that doesn't just limit you to join data sets across obviously S3 and Redshift and other things in the future, but it can also scale to other new connectors because Facebook, which supports Presto, keeps adding new things. So while we do use Spectrum occasionally when we really need to join only within Redshift and S3, we do envision a world in the future where we may need to also join across other data sets that we might have in other data stores. And Presto is a very robust open source project. We felt like in the future, if we were to do our own Presto on top of EMR, instead of using Athena, that might be a flexible option for us. That was the reason.
How do you decide to choose between Elastic MapReduce and Glue? What are the cases for each?
What was the question?
Well,
which one do we
that's
do?
the most.
EMR.
That's the one. Okay.
Yeah.
Cool.
Yeah.
Somebody snuck a vote in last
yeah,
minute.
Yeah. So I think this is one of the things that I kind of worked on. Initially, it's hard to kind of get a track of where to use which, and this is something that we learned over time. So I think Glue, the way we see it, is kind of like the AWS Lambda for the Spark environment. If there's something that you just need to do, has minimal overhead, it's just a simple script that you want to transform gigabytes of data from one place to another, I think Glue is the perfect option since you need minimal configuration to do that. If there's a really large workload that you're working on top of, where you need to fine-tune a lot of things, you need to fine-tune the resources you're using, you need to fine-tune how much memory you're using, or a particular instance type that you really like, and you want executor logs, you want driver logs to see how things are going, I think EMR would be a better solution as you start moving into terabytes of data and want some of these fine-tuning configurations. That's when you go for EMR.
You guys collect a lot of data. How much of it do you never touch? As accurate as you want to be, or just roughly?
Yeah, so I think we've been pretty good about only building downstream data sets for those use cases that actually come up. So the cool thing about the data lake as opposed to a traditional data warehouse is that even though you may dump a bunch of raw data into your data lake, you actually transform and utilize that data only when applications come up. So when a new application comes up, you still have the raw data, you can transform it for that specific use case and make that available. So there's obviously data sets that we ship into our S3 buckets, like our server logs or ELB logs, that are used rather rarely, but there are certain use cases. For example, in the case of ELB logs, we do have a use case that we want to monitor the latencies on certain endpoints. For that use case, we actually looked at that very frequently. So while it's true that there are certain data sets where certain aspects of the data are not looked at very frequently, for all the downstream views on our data that we've exposed either via Athena or via Looker, we only build them when we have a user in place. And we can do that because we take the data lake approach, which is you have this raw data layer, and you transform it as you need it, as opposed to always thinking about dumping the data in the format that you think it'll be used. Because you're assuming things down the road which may not actually come to fruition, as this question points out.
Why did you choose Looker over things like Metabase or Periscope data? What were the features that really drew you to Looker?
It's a good question. I mean, there's a lot of, it's hard to point out exactly, there's this one tipping point feature that, makes you decide one versus the other. For us, it was, just talking to a lot of people internally. A lot of the people who have worked at Robinhood have some experience with Looker in the past. They felt pretty good about it. It integrated with all our data sources. It plugged into everything that we're trying to build with the data lake. So given its flexibility, given that there were a lot of internal customers who were on board with that idea already, it seemed like a natural fit for us.
And based on your experience using Airbnb's Airflow, what are some of the pros and cons?
Right, so I can take that up. So I think Airflow certainly has a lot of pros. As I spoke, it certainly automates a lot of different things that are really difficult or cumbersome to do manually yourself. But I think there are definitely some cons with any project. Like for example, some of the things, since we're running on a slightly older version of Airflow, a forked version, we saw some things like that were not intuitive, like how the scheduler schedules certain things, like it's done in a data science way. That's really hard to understand that like it schedules for 24 hours before whatever your actual workload is, if your workload is for a daytime. There's some logic in our version which actually takes it for granted and is non-configurable, that anytime you create a DAG with like an earlier startup point, it'll try to backfill everything in the meantime. These are things that are fixed over time, and I think the best part about Airflow as compared to like some other solutions is that all the code is out there, the community is really actively developing on top of this. So if I do see a problem in Airflow at the end of the day, it's something I can just write some code to fix. So I think that's really configurable, and that's the thing that sticks out to me at the end of the day. Every software will have bugs, but the extensibility that I can just go and fix it like really quickly, I think is the best part about it.
What happens when someone comes to you and they want access to data which hasn't made it into the data lake? How do you, and it's not available in Looker, what do you do?
I think there's a whole process that goes that we have to go through. We want to understand the exact use case they want to be using. Do they want to make ad hoc queries to the research environment, or is this something that they just want to visualize through Looker? And based on that, we will basically design a workflow in that first we will see where this data is actually coming from. Is it a batch or streaming use case? We'll start dumping that through Airflow or SQL or whatever the use case be respectively. Once that is in the data lake, we will basically just create a DAG in Airflow that orchestrates all of this workflow. It runs the crawlers or runs the add partition commands, and basically then goes on and runs the Spark job. So somebody has to go in and write a custom Spark job for this particular data set based on how the users want it at the end of the day. Right now, a lot of the brunt of this work is borne by the data team, but we have a hope that we can make this development environment really flexible and really easy to use, such that engineers across the company, anytime they want access to some data, if they're technical users, they can do it themselves. So we've tried to abstract away a lot of like these common sense things like adding partitions or discovering new data using crawlers. We've just turned these into Airflow operators that people can easily use in their job.
You want your QA and staging environments to match production, so how do you replicate this data, the volume of this data, down to lower environments?
So,
what's your strategy?
Yeah, I mean, I think it's very difficult. You don't want to be duplicating all the data downstream, because then you're paying twice the amount because you're storing the data again and again, right? So what we try to do is, you've leveraged things like the Glue development endpoint that allows developers to kind of talk a little bit to sanitize production data, so they can estimate the scale of the operation going on. Then they can test at a much lower volume of data in the QA and staging environment. So we don't replicate the exact volume, we have a much lower volume. But then they know that the logic is going to be correct, right? There's still some things that you only know when it hits prod. For example, if you're looking at the events data set and you want to operate over terabytes and terabytes of data, the exact runtime of your job and the exact implication of the data SKUs that result as a result of your Spark job will only really be visible at that scale. So yes, there's definitely cases where you can't replicate everything at the lower scales, but most of the logic issues, most of the issues related to bad structure of your code, et cetera, can be found out at the QA and staging layer.
Can you share some of the complexities of transformations in Spark, and do you have any runtime benchmark comparison numbers when you're comparing it to Redshift?
So we use Spark and Redshift for different things here. So I'm going to try to answer the question as I understand it, even though this is not exactly how we look at it. So Spark is used to handle data transformations in ETL, while Redshift is, once we have done these transformations, it's there for analytics or reporting workloads. So we look at it more from the querying perspective. So an equivalent there for us would be something like Athena. And what we've noticed is that while Redshift is great, it's really fast, you're obviously paying for the standing compute with the storage, so you kind of have to keep both moving up in lockstep with each other. So for a lot of use cases where people really need to ask a lot of questions really frequently, or reporting workloads need to have a very tight SLA, Redshift is great. You're getting value for that cost. But cases where it's more ad hoc, we're willing to slow down our queries a little bit to kind of separate that compute and storage that we talked about. And there, Athena, even though the query performance itself is slightly slower, if you look at both cost and query performance as benchmarks that you care about, it still works out to be better.
You're nowhere near the end of questions, so here we go. How do you manage your EMR clusters? Are they transient or persistent?
Right, so I think I worked on this part, so I can answer that. So I think since our use cases for EMR right now are not consistent, this is usually used for backfill purposes. So these are just transient clusters that we bring up with the exact configuration that we think we need for a particular use case. So right now these clusters are transient, but I think like we're getting to a point where even our daily workloads are getting to a point where they need these kind of configurability, they need these kind of computation power. So we are getting to a point where we are going to look into having a persistent cluster, but right now these clusters are just transient.
How do you handle incremental updates of mutable snapshot updates?
Right, so I think the way we do that is we take a complete snapshot of the entire database every time we do a snapshot. We don't do any incremental updates. We don't do a delta update on top of this. I think this gives us, while this is kind of, we're redoing a lot of computation in that like we're just taking most of it is redundant between different snapshots. I think this gives us a really cool ability for tables that are mutable, that don't retain their original form. This allows us to do some things like, for each snapshot, we can take a look at what the table looked like at a certain point in time. So if we're taking a snapshot of a mutable table each day, we can see over time like how this table changed over time and do some queries that we won't be able to do if we just maintain the latest snapshot.
What technologies are you using for the validation layer? And did end users, like analysts and scientists, also get to write their own rules for their ETLs?
Right, so I think this is a very good question. The reason like we're trying to do, we made this framework as customizable as possible. Since S3 is like the wild west of the storage layer, it'll let you store anything, we're trying to bring a lot of the guarantees that come with a relational database, like null checks and unique constraints. A lot of primary key constraints that come out of the box with systems like Postgres are not available in S3, and for the data you're storing in S3. So what we try to do is like we try to implement most of these checks out of the box. So if there's a data set where you want to make sure that there's an enum that all the values fall between these set, you can just make sure, just use that out of the box with your custom configuration. But we understand at the end of the day that each data set is different, and the use cases will be different, and common sense things you want to check for will be different. There might be different things you want to check that like, oh, these two tables should be the same size, whereas this should be strictly greater than the other. So for these use cases, we define a custom use case or a custom query where you can just specify whatever query you want to make, and it'll just run that and make sure that like the result is in line with whatever your configuration is. To come up with these queries or like what a common sense is for some of the data sets, we work with our data scientists and our end users to see what actually makes sense for a certain data set before we actually set up these checks.
Why did you have to build some of your ingestion layer yourself?
So we actually chose to do this for two reasons. One, we wanted control over how the data gets into S3. From a data lake perspective, the way we understand it is that once the raw data is in S3, since it's the raw data, any transformation that we need to do on top of that can be done or changed, and we still have the raw data. So nothing is lossy in that sense. So having control to make sure that everything ends up in the data lake in the correct format and its raw format is something that we wanted complete fine-grained granularity over. If any bugs are introduced there, we wanted to know exactly what's going on. We wanted to make sure that we were very, very deeply understanding every logical piece there. So we didn't want to go and outsource this to some other company that would take data from someplace and push it into our lake. Because if something went wrong there and the data didn't end up there, if it's not in your data lake in the raw format, you don't have that data anymore, right? It's gone forever. So yeah, we wanted complete control of that. So it was primarily from that perspective.
We're going to do a couple more and then wrap it up, but you'll be around afterwards to answer the rest of them.
Please.
So did you do any performance comparisons between Athena and Redshift Spectrum for user-facing queries?
So I think I can take up this part since I looked into that. I think the way we looked at it is that there were different use cases that these would be used for. Let's say that we already have a Redshift cluster standing up. There's no point in using Redshift Spectrum for queries that are only in S3. Redshift Spectrum, instead, like since you already have the compute for the nodes over there and it would just spin up other nodes that it needs to do the computation, it's best to use it or reserve it for the use cases where you want to do join operations between data that is stored in Redshift and data that is stored in S3, because there's no way you can just use Athena for that. And it's instead better to use Athena just for the use cases where you actually just want to query the data that is already present in S3 and don't need any interaction with Redshift. So there's no way, or there's no reason to actually get Redshift involved if the data is not related to that. And if we were to only use Redshift over here, then we are kind of defeating the same purpose of like storing or decoupling our storage and compute. So we kind of look at these for different use cases, so we don't want these to collide together.
We might be able to make all three. Let's see how quickly we can do this. How easy is it to debug your ETL process using this architecture?
Okay, I can take this up. So basically, the problem that we saw over here at times is that initially it's kind of hard, and there were two factors to this. I think a lot of the engineers were using Spark for the first time, or a lot of the engineers were working with these big data technologies for the first time. So there was an initial ramp-up process as well. And for some of the tooling, we have found that debugging is kind of difficult. For example, with Glue, since we don't have detailed executor logs, or at one point in time we didn't even have visualizations into how different executors were utilizing their memory, and if one was spilling to disk too much. So that kind of made debugging a little difficult at that point in time. But there are certain alternatives that Glue has come up with, such that they came up with development endpoints that were that allowed us to at least test the code, and they have added much better visualization tools on top of that. But I agree that this is a problem that we did face concerns with, and this is something that we thought that were better solved with EMR. If we were writing something completely from scratch, it's something that would have these kind of failures where we were spilling to disk, using too much memory. These kind of issues, we think we try to outsource them to our EMR cluster instead of using this on Glue, because we have a lot more debugging ability over there. But I think these are things that, as we've talked with the Glue team, these are things that are on the roadmap, and we'd be excited to test them once they're out.
End-to-end, what's total processing time from when you ingest an event to visualization in a dashboard?
I think both of these questions are related, so I'll just kind of answer both of them in one go. So most of our data ends up nightly in our data lake. There's some that ends up much more faster based on the use cases. So we work with either the provider of the data or the users of that data eventually to figure out what are the SLAs that are acceptable. Mostly data is available every day. So the previous day's data becomes queryable, and analyzable the next morning. How long does it take for that data to end up to Looker users? Looker, obviously you have to add a model layer on top of it. The awesome thing about Looker is it gives you a lot of flexibility. So we'll work with the end use cases at that point. So let's say you want to run a cohort analysis over this data for some reason. We'll actually understand what is the cohorting analysis you want to do. And based on that, we'll model out Looker in that pattern. And so, it's just a question of getting the person who wants that specific answer and the kind of analysis they need into the same room. And once they've given it to us, it takes very little time to build that out for them. So it varies. It varies on the use case. It varies on what they actually want to do. If they want to do something really complicated, it might take a little longer. But usually, as soon as the data is available, we can make it queryable via Looker.
You survived the 37 questions. Nicely done.
Thank you very
please,
much.
round of applause for Robinhood.